Welcome to the lecture Solar Radiation and Solar Basics. The learning outcome for this lectures are to have an overview about the characteristics of the Sun and solar radiation. As well, you will learn some definitions. In the second part of the lecture I will talk about the test reference year, shading and tilted surfaces since they have a huge impact on the solar yield. The Sun is the central energy producer of our solar system. It is a 1.4 million kilometer diameter sphere with nuclear fusion taking place continuously in its center. The solar radiation emitted by the Sun has a temperature of approximately 5500 degrees. The Sun has an age of around 5 billion years and its lifetime is expected to be 10 billion years. Over a distance of 150 million kilometers, just a small fraction of the energy produced by the Sun hits the Earth and makes life possible. Solar radiation drives all natural cycles and processes such as rain, wind, photosynthesis, ocean currents and several others. The incoming solar radiation energy in 4 hours is enough to provide the complete yearly world energy demand. Before we will go ahead with the basics of solar engineering, we need to clarify a few definitions. When we talk about beam radiation, it is meant the solar radiation received from the Sun without having been scattered by the atmosphere. It is known as direct solar radiation as well. In contrast to this, diffuse radiation is the solar radiation from the Sun after its direction has been changed by scattering by the atmosphere. The sum of diffuse and beam radiation is the total solar radiation, or so-called global radiation. Very important terms are irradiance and insolation. Irradiance is the power incident on surface and it is also called radiant flux density. In contrast to that, insolation identifies the solar radiation energy received on a given surface in a certain time. The lost definition lead over to the next slide. The solar constant. The solar constant is the energy from the Sun per unit time received on a unit area of surface perpendicular to the direction of radiation at mean Sun-Earth distance outside the atmosphere. Due to the ecliptic revolution of the Earth around the Sun, the extraterrestrial solar radiation is changing with the time of year. The solar constant equals 1367 watts per square meter. The duration of the sunshine as well as the solar irradiance is depending on the time of the year, weather conditions and on the geographical location. The amount of yearly global radiation on a horizontal surface may exceed 2200 kilowatt-hours per square meter in the Sun Belt regions. In Northern Europe and Canada the maximum is about 1100 kilowatt-hours per square meter. Depending on the latitude there is a huge variation of the daily solar radiation density. In regions close to the equator the solar radiation density is more or less constant, while in regions far north or far south there is a peak in the summer. That means that you can hardly cover the domestic energy demand with solar systems in regions far the equator without oversizing the system. Test reference years are generated by selecting time spans of measured climatic data from a number of measured years for one location in such a way that the long-term monthly averages of all climatic data for this location are matched. Using measured data ensures that the weather fluctuations of the region are correctly represented. Generating test reference years is very time-consuming and consequently they are often very expensive. They are necessary for designing the solar system and calculating the solar yield. In POLISON the weather data is automatically calculated by entering the location of the system. Okay, now we want to talk about shading. Shading has a main impact on the solar yield. It depends on the sun path and on obstacles in front of the collectors. To make it a little more visual I will show you how to define the shading in POLISON. After starting POLISON and creating a new project, click on Location of the System. Then choose the location of your system and click on Edit for the horizon. First you can import the horizon line through clicking Media Norm. Under Obstructions and Mutual Shading you can define new shadings. it is the best to play a little bit around to get familiar with the function. Under sun path you can now change the day of the year and the time. You will see when the sun is behind an obstacle or your collector is free of shading. Another important property of a solar system is the orientation and slope of the collector. Again, it is necessary to clarify some definitions. Latitude describes the angular location north or south of the equator. North is always a positive angle while south is a negative angle. The azimuth angle is the angle between south and the orientation of the surface. To the east it is positive and to the west negative. The slope is the angle between the plane of the surface and the horizontal. It is called tilt angle as well. To optimize the orientation and slope for a collector, it is necessary to know the latitude. On the northern hemisphere the collector should be installed south-facing and for the southern hemisphere north-facing. A rule of thumb is to use the latitude as slope angle. On the figure on slide you can see the influence of tilt and the orientation on the maximal solar output for latitude 35. Okay, now it is time to summarize the most important points of the lecture. You learned that 4 hours of sunshine can cover the complete world energy demand. As well, you learned that the global radiation is the sum of beam and diffuse radiation. A figure you should have in mind is the solar constant. It equals 1367 watts per square meter. About the solar radiation, it is good to know that it varies over the time and that it depends on the local latitude. Shading and weather have a main impacts on the solar yield. With PLISN you can take both into account, the shading and the from the weather data calculated test reference year. You should never forget that the optimal orientation for a collector on the northern hemisphere is south-facing and on the southern hemisphere is north-facing. As a rule of thumb you can say the optimal slope is equal to the local latitude. Thank you for attending the first part of the second lecture. In the second part of lecture 2 I will talk about the basics of photovoltaic systems.